Welcome and hello. This is a video tutorial on HEC HMS, and in this lesson, I'm going to talk about snowmelt, specifically the snowmelt using a temperature index or gridded temperature index. This is part of subbasins, so subbasins, snowmelt, temperature index, and gridded temperature index methods. All right, so what I've done already, I have on the screen here is a watershed that has been delineated into a number of subbasins. I only need to really talk about one subbasin at a time to get the message across regarding snowmelt method, temperature index. So we're just going to focus on this downstream most subbasin 45. The most common way to measure the water content in a snowpack is what is called the snow water equivalent, or SWE. You may have seen that SWE labeled in HEC HMS before. This is the depth of water in the snowpack if the entire snowpack had melted. So if you have 10 feet of snow, then the SWE may only be 2 feet of water if that snowpack completely melted. It's sort of based on snow density. I'm going to go ahead and start by clicking the subbasin 45 here. And then Subbasin 45 is also showing up here in the Watershed Explorer. Below that is the components editor, and I have this snow method right here. It's really referring to snow melt method, so I may use the term snow method or snow melt method. I mean the same thing. Our options are energy budget, gridded energy budget, temperature index, gridded temperature index, and gridded hybrid. And of course, none is the default. In this lesson, I'm going to talk about the temperature index and gridded temperature index. So let's go ahead and start with temperature index. I should also mention that you may not need to use snowmelt method in your HMS model. The only time you would need to use the snowmelt method is if you're going to have snow during the simulation, or if your watershed starts with snowpack, then that snowmelt would have to be taken into account. All right, so I have temperature index selected. Now I'm going to go up and select the subbasin 45 here and expand by clicking the plus symbol to show the temperature index here is my snowmelt method. So the same thing is true if I click on the snow tab here. That's what happened when I clicked the temperature index. If I go back to my subbasin tab, I should mention that the gridded temperature index has a lot of overlap. In fact, the gridded temperature index method separately computes each grid cell instead of averaging the entire subbasin. All right, so let's go back to the snow tab. Now, if I go ahead and right click on this temperature index, I have an option to add an elevation band. So I'm going to do that. And then if I expand the temperature index, I can see my band 1 right here. And then I can keep doing that. I can add band 2, band 3, and then these bands, if I click on them, they have their own data. So this represents an elevation band from a certain elevation up to a certain elevation. And then the next band would start at that next elevation and go upwards. And it's a way to group the different temperature index values into areas within the subbasin. So you may only have one band, and that's fine. And then in which case your percent area right here would be 100%. But if you had multiple bands, you may have 50%, and then band 2 maybe say 25, and then band 3 maybe 25 as well. So I'm back to band 1. And these bands representing areas within the subbasin, they don't have to be contiguous. You could have band 1 over here, here, and here, and then band 2 over here and different places. I can also delete the band, so I could just right click, remove elevation band. It asks me if I'm sure I want to remove band 3. So this sort of works as a stack. It will only delete the last one that's been added. And then I'm down to band 1 and 2. So I'll say band 2 is 50% area. And if you mess up with your percent areas and they add up to more than 100 or less than 100, then that'll be normalized in the computations. Okay, the other parameters here that we need to specify for a band is the elevation. So this is sort of like an average elevation, and it could be a weighted average based on the area, or the elevation could be sort of the average between the max and the min for that elevation band. You may want to use a lot of elevation bands in your subbasin if there's a lot of elevation variation within the subbasin. But if you only have a very flat subbasin, then one band would probably work just fine. The next parameter here is the index, and this represents the precipitation index, so that there can be different variation of precipitation between the different bands. And you're probably going to have a little bit more precipitation at the higher elevations. If this precipitation index in inches is entered, then you'd have to enter that value for all the bands. And then you'd also have to enter it up here at the subbasin level. Okay, so back to band. The last 5 parameters here are all initial conditions for the initial snow. So if you don't have any snowpack in the subbasin or in this band, at the beginning of the simulation, then you can just go ahead and click no or 0 for all these values. And then actually the temperature would be 32 Fahrenheit and then 0 down here. But I will mention these. Here's the initial snow water equivalent, and that equals the depth of water that would result from all the snow in the snowpack melting. Next is the initial cold content in inches, and this refers to the amount of energy that is required to raise the temperature of a snowpack to the melting point. It's equal to the depth of the snow multiplied by the snow density multiplied by the specific heat of ice multiplied by the number of degrees below the freezing point. So if you do the math, it actually has units of energy per length squared. I'm seeing inches right here, so I'm not exactly sure how that would convert, but just go ahead and do the math. The initial liquid water, which is the next one down, represents the depth of water in the snowpack. It would most likely be 0 unless that the temperature is right at the melting point of 32 Fahrenheit. Next is the initial cold content, antecedent temperature index, and this equals the snow temperature near the surface of the snowpack. So if you're unsure, just go ahead and put 32 Fahrenheit or 0 Celsius. And the last one here is the initial melt antecedent temperature index in degrees Fahrenheit days. This is going to equal 0 if there's no snow or if the simulation starts after a period of cold weather with freezing temperatures. And it's going to be a number greater than 0 if the simulation starts during a thawing period where the temperature is above the melting temperature and based on the temperature above freezing and the number of days. So that's the data that's required for all these bands when using the temperature index snow method. Next, we need to actually fill out the data for the main tab. So I'll click on the temperature index record here. This first parameter is index. We talked about all that already. That's the precipitation index in inches. Next down is the px temperature. If the air temperature is less than this px temperature, then the precipitation is snow. If the air temperature is greater than this px temperature, then the precipitation is rain. The base temperature here is going to be set to 32 Fahrenheit, and this base temperature is used to calculate the temperature index. So the temperature index equals the air temperature minus this base temperature here. ATI coefficient is the antecedent temperature index coefficient. I'm going to talk about that a little bit later when I talk about cold limit, ATI melt rate function, and ATI cold rate function, because I think they all kind of go together. Okay, next up is the wet melt method, dry melt method, and rain rate limit. So I'm going to talk about all of these three together. The rain rate limit determines whether or not the snow melt method uses the wet melt method or the dry melt method. If the rain intensity is greater than the rain rate limit, then the wet melt method will be used. And if the rain intensity is less than the rain rate limit, then the dry melt method would be used. So if I put a value of 0, for instance, then we would only use the dry melt method if there's 0 rain. If there's any rain and the rain rate method is 0, then we would use the wet melt method. Okay, so the values we can set for these methods can either be constant or annual pattern. So if we stick with constant, we just go ahead and type in a number here, and probably not 1, but just a number. And then if we select annual pattern, what we have to do is select the pattern from a gridded data set. So right now I don't have any gridded data sets in my watershed, but I can do that. I'll go up to components, paired data manager. And then for the type, I want to select the parameter value pattern. It's fifth from the bottom, at least in my version. So I'll do that. I'll click new, and then I'm going to give that paired data set a name. By the way, I'm just covering paired data sets very brief here. I've made a separate lesson on that, lesson 4. It's called paired data. So by all means, check that out. But I'm going to go ahead and type or paste in the name of my paired data set. I'm just going to call it wet melt rate TI1 for temperature index, and then create and close. Now up here in the Watershed Explorer, I have a paired data directory, and inside that parameter value pattern directory. And now we have that wet melt rate TI1 pattern that I put in. Now down below in the components editor, we have more work to do. We have to specify that this is for snow melt for the category. For method, this is temperature index, and that's why I put a TI here in the name. And then the parameter is going to be wet melt rate. After that, I can select the units. Next, what I would end up doing is specifying the data itself. So manual entry or HEC DSS file are my options. So if I go with manual entry, for instance, I have data here. And I've already populated this data from earlier in the preparation, but it would just be a blank table. You'd specify a date and then the value and then the next date and the value, and then that'll be used during the simulation. All right, so let's go back to our subbasin and see if we can now put in that wet melt rate. So I click the subbasin, then click Snow tab, and our wet melt rate, if I click annual pattern, it now has a record for wet melt rate TI1. This is the paired data set that we just put in. And then for the dry melt method, again, we can use fixed or annual pattern. We've already seen the example of an annual pattern up here. The only difference is we'd select dry melt instead of wet melt. And then another option is ATI function. If we select ATI function, it's now looking for an ATI function from paired data, except it's going to be a different type. It's going to be an ATI melt rate function. So let's go paired data manager and then scroll down to find the ATI melt rate function, click new, we'll give it a name, and then create. So now in the paired data directory, we have an ATI melt rate function directory, and here's our ATI data. And then we would select the data source, either manual entry or a DSS file. So I'm not going to do that again. Let's go ahead though and check to make sure that that worked. So I go to Subbasin, Snow tab, and then ATI function. Yep, and it has our ATI melt rate that we've put it in. The next few parameters I want to discuss together, and they are cold limit inches per day, the ATI cold rate function, cold rate coefficient, and then from above that ATI coefficient. So I think these four should all be sort of grouped together. The ATI cold rate function, which is right here, is used to calculate a cold content from the current cold rate index. Now, if the precipitation is less than the cold limit right here, then the ATI cold content index is set to the temperature of the precipitation. However, if the precipitation is greater than this cold limit, then the ATI cold content index is set to the antecedent uh, index. Right now, I don't have any options for this ATI cold rate function, so we can add one, and that's going to be again in the paired data manager. So we'll go paired data manager and then scroll down to ATI cold rate functions. We'll click new, give it a name, create, and then back to our paired data. We now have a directory for the cold rate function, and then here it is. And we would just go ahead and again select manual entry and enter the data that way, or use a DSS file. Okay, so let's go back and make sure that that worked. Here is our ATI cold rate function one, and that is how the cold content is calculated. All right, we have a few more parameters here. Water content percentage. This represents the amount of melted water that must accumulate in the snowpack before liquid water actually starts to contribute to the runoff or to the infiltration. So it's going to be a small number, maybe like 3% or 5%, according to the user's manual. But just imagine that a large snowpack will have a little bit of snow melt inside before it actually contributes to runoff. The last two is ground melt method and the actual ground melt rate. So these two are considered together because, for instance, the ground itself may offer a little bit of warmth and serve to melt the snowpack. So the options are fixed value and annual pattern. If we go fixed value, we would just type the value in here, like a 1 inch per day, probably not that much. And then for annual pattern, we would select the pattern here. And as before, we got to enter a paired data set. So let's go ahead and do that. I'm going to go up to components, paired data manager, and then we're going to select the parameter value pattern, which is right here. We already have our wet melt rate. We're going to enter a different type now. So there's the name ground melt rate for temperature index number one. So that's entered right there. And then let's go ahead to our paired data set and then parameter data. Here's our ground melt rate TI paired data set. And then what we'll do here is, yeah, manual entry or DSS file. Precipitation, we're going to go with snow melt for the category. And then temperature index is the method. And then the first option, the default here for ground melt rate is the one we want. So let's go back and just confirm that that's now an option for us. Snow tab, ground melt rate down here at the bottom. Okay, so that was all the parameters for using the temperature index snow melt method for a subbasin. If we want to look at multiple subbasins that use that same temperature index snowmelt method, then we can go up to parameters and then snowmelt and then select this temperature index. Right now, I only have one row in this table, but if I had multiple subbasins all using temperature index snowmelt method, I would see it here and I can make global edits. So this is what's called the global editor. And there's a lot more columns. I'm only seeing about half of them here. So if I scroll to the right, you're seeing more columns over there. All right. So I'm going to leave subbasin 45 as the temperature index snow method, but I'm going to use this subbasin 44 just to the right, adjacent to it, to the east. And I'm going to use this one for the snow melt method gridded temperature index, and then click save. Now, just like the temperature index method, I can go up to parameters, snow melt, and now select gridded temperature index. It's only going to show me subbasin 44, but I just wanted to mention that there's a lot more fields, so I can continuously scroll to the right. I would kind of like the subbasins column to be fixed so that I can always see that regardless of where I'm scrolling, but just a preference. All right, so let's close that and describe a few of the differences that between temperature index and gridded temperature index. What's different between these two different methods is that the gridded temperature index has equations for simulating snowpack are they're computed separately for each grid cell with separate precipitation and temperature boundary conditions instead of using an average area value or different elevation bands. So for instance, if I expand on subbasin 44 and I click on gridded temperature index and then right click, I can't add elevation bands. It's based on a grid cell coordinate system, not on elevation bands. I go ahead and select this snow tab, and we're seeing all the data in the components editor down here for snow related data for subbasin 44. And the only difference we see is at the very top here. So for subbasin 45, we had the precipitation index, and then after that, px temperature and all the other things. For subbasin 44, it's all these initial conditions instead of the precipitation index, and then the px temperature, and then everything else down the same. So what we're seeing here for values are the initial snow water equivalent type, the initial cold rate coefficient type. You can read them yourselves. And the separate values we can choose are the default value, the constant value, or the parameter grid. So the default value is what they're all set to for default, and that's just zeros basically. The user's manual does describe exactly what these values are, but basically for the snow water equivalent, it's 0 inches or 0 millimeters. For the cold rate coefficient type, it's 0 inches or 0 millimeters and so on. If I had an actual constant value, I would select constant value here, and then I would type it in here. The whole point of using a gridded temperature index snowmelt method is to be able to use parameter grid data. So if I select parameter grid data, then I would go ahead and select the parameter grid from the gridded data set. We've done that enough times in this video. You get the idea. The user's manual talks in depth. It's very verbose and sometimes repeats itself across different snowmelt categories, but better than not enough information. So if you're interested in learning more about the snowmelt method, I will leave a link to the page in the user's manual that describes all of this. But that was it for this lesson. We talked about the subbasins, specifically snowmelt methods, the snowmelt methods of temperature index and gridded temperature index.